Brian Lewis as the speaker. He's a master's student at the Department of Applied Mathematics here, of course. He works towards his PhD with Professor Gregory Laykin. He received his BS in Computer Science in 2003 and his Master in Applied Math in 2009. He was with Northrop Grumman Corporation from 2003 to 2010 and was an intern with Western Geeko, part of Schlumberger in 2011. His interests include approximation algorithms, signal processing, computational optical and seismic imaging, and inverse problems. So, welcome.
Thank you very much. And thanks for coming. So today I'm going to talk about a new algorithm for the accurate propagation of light. So the outline will be to introduce the problem, and it's an old problem, so there's quite a few existing algorithms for solving it, so I'll spend some time talking about them, our new method, and then what we plan on doing in the future. So the problem we want to look at is to numerically propagate coherent light between parallel planes in the simplest medium imaginable, a linear, isotropic, homogeneous medium. So the propagation in that kind of environment is described by the scalar-Helmholtz equation. So in order to simplify the constants, we'll set our wavelength equal to 1, and that way we'll measure all distances and wavelengths. And the problem we want to solve is a boundary value problem. If you're given the field in a plane, which we'll always take to be z equals 0, we want to know what's the field in some plane to the right, z equals z naught. So as a point of notation, I'll have to use two-dimensional vectors and three-dimensional vectors. So a 2D vector will always be lowercase bold, a 3D vector will always be uppercase bold. So now we'll assume that our solution satisfies Sommerfeld's radiation condition, which gives us the outgoing solution to this problem. And then, if you're given your boundary data, which I'll call F, in the plane, the Rayleigh-Sommerfeld formula gives us the answer we're looking for. It says you need to convolve your boundary data against the appropriate Green's function, and that gives you the field anywhere you want it. Now, you can always represent this in the Fourier domain. Since it's a convolution, you just apply the Fourier convolution theorem. So we'll let f hat be the Fourier transform of our boundary data. And then what this says is if you want to propagate, you take the Fourier transform of your boundary data, you multiply it against its propagation kernel, and do the inverse Fourier transform. And so right away you can see important features about this problem. One particular one is that spatial frequencies outside the unit disk decay exponentially fast as a function of z. And it's well known that after only a few wavelengths, these evanescent waves quickly decay to levels lower than the detection threshold of a lot of optical equipment. I'll talk a little bit more about what that means later, but it's worth keeping in mind now. So what I'm going to be concerned about is to numerically evaluate this integral. And the thing that makes this tricky can jump out at you right away. So notice that the two-dimensional Fourier transform of the field U in the plane z equals z naught is given by the product of the Fourier transform of our boundary data and this propagation kernel. So for large z, or even medium-sized z naught, this product becomes highly oscillatory. And dealing with the highly oscillatory nature of that kernel is the primary difficulty in these problems. So I've talked about this a little bit before at a poster session, and the almost universal response is, isn't this a solved problem? So I need to address that right off the bat. And it's a reasonable response because there's a few fairly obvious methods for trying to solve it. Probably the first thing that would pop into your head is to use the convolution theorem in the Fourier domain. So this says for step 1, if you're given a propagation distance and samples of your boundary data, you should use the DFT to get samples of f hat, multiply those samples by the propagation kernel to get samples of u hat, and then use the inverse DFT to get samples of u. And that works just fine until z naught is large. And because optical wavelengths are so short, z naught is almost always large. And when that happens, the Fourier transform of our field, u hat, becomes highly oscillatory. And you need an impractical number of samples to get high accuracy. So let me illustrate this with an example from the literature. So this is one of those classic problems, diffraction by a narrow slit. So here we have a slit width of 3.2 millimeters. You illuminate it with a 0.6328 micron wavelength, and you want to propagate the field 3,200 millimeters. So in wavelengths, that corresponds to propagating about 5 million wavelengths. And it's that 5 million number that causes the trouble, and that makes the kernel be highly oscillatory. So to get a handle on that, let's estimate the number of samples that would be required to obtain an accurate solution. So because that boundary data is constant in y, the problem reduces to the evaluation of a one-dimensional integral. You can show in this case that the evanescent waves aren't significant, so you can replace the infinite limits of integration by -1 to 1. And now, a simple calculation shows that the shortest oscillation of u hat, of that integrand, has a width of about 2 times 10 to the -14th. So Nyquist tells us that we would need to ensure at least 2 samples per oscillation. And so that works out to needing 2 times 10 to the 14th samples, which is obviously very impractical. And because of that, we need to look for alternative methods of evaluating this integral. So one of the more popular approaches is a multi-step algorithm. Sometimes it's not given a name at all. Sometimes it's called the modified convolution approach. I'm going to call it the MCA because I need to give it some name. And it works like this. Given the number of input samples, you can find the maximum distance you can safely propagate before the field becomes too oscillatory. So call that Z max. Then you divide your total propagation distance up into smaller steps. I'll call it delta Z1, delta Z2, blah, blah, blah. And so each one of these smaller steps is smaller than this Z max. And then for each step, we do 2 things. First, we propagate the distance delta Zm, and then we do a zero padding operation in space. And the zero pattern operation in space has the effect of filtering out the high frequency oscillations in the Fourier domain. So step 2 here is the critical part. It does what we've wanted. It reduces the oscillatory nature of our field in the Fourier domain, but you pay a price for that because every time you do the zero padding operation, you effectively introduce a square pupil or square aperture that's artificial. And so as the light propagates numerically, you introduce artificial diffraction effects from these square pupils. And that results in artifacts in your final answer. So does the algorithm work? In order to decide that, we need to do a quantitative comparison of the result. We need to compare the output of the algorithm with an exact answer. So it turns out in this particular case, you can obtain an exact answer. And one way to do that is to substitute the Jacobi-Anger expansion into the Rayleigh-Sommerfeld integral. And that gives you a series expansion for the exact solution. So these coefficients A are defined by this integral. And what's nice is they decay very rapidly. And the particular form of the integral allows you to use the DFT to efficiently and accurately calculate those coefficients. So what this means is we can evaluate the true solution to any desired accuracy. So to test the MCA, we evaluate them so that the field is correct in 9 digits and compare the output of the MCA with the exact solution. The answer is, in the paper that this example comes from, the authors proposed using 512 samples, and it gives you an answer that's correct to about 1.5 digits. So on the left, I'm showing you the true field in blue and the approximation from the MCA in red. And then on the right, I'm showing you the magnitude of the error. So the thing to notice is that the error is substantial right at x equals 0. That's right on the optical axis. You might hope that the errors are confined to the off-axis side lobes where you're generally not so interested in the answer, but that's simply not true. The error is of about uniform magnitude everywhere. It's substantial right on the optical axis. So the accuracy is not great, but it's not terrible either. So a reasonable thing to hope is that by increasing the number of samples, you would get a more accurate answer. Unfortunately, that's not the case. So here I'm showing you the plot of the error versus the number of samples. And as you double the number of samples at first, the error does go down. But eventually, it starts growing with the number of samples, which is counterintuitive to say the least. So what's happening here is that as you introduce more samples, that Z max, the maximum step size, becomes smaller. You have to take more steps, which means you have to introduce more of these artificial square apertures. So eventually, the artifacts caused by these square apertures counteracts the hoped for increase in accuracy you wanted by introducing more samples. So a few thoughts on this algorithm before I move on. It's important to notice that this quantitative analysis was only possible because of this one particular choice of boundary data. In more realistic situations, you obviously don't have an exact solution to work with. And so it's quite difficult to know if the solution you just computed is reliable. That's not a failing unique to this algorithm. Virtually no propagation algorithm comes with an error estimate. So the MCA is certainly suitable for applications that require low, say, single-digit accuracy. And I want to be very fair, those kind of applications do exist. So the last idea I want to talk about before I move on to ours is the idea of convolving directly in space. And this idea is motivated by the observation that when you propagate long distances, the kernel in space becomes less oscillatory. So here I'm showing you the real part of the kernel from the previous example after you've gone 3,200 millimeters. And it's not oscillatory at all, and so integrating against a kernel like that is easy. Unfortunately, for more practical distances, say 15 centimeters, the kernel is still highly oscillatory. So this is what it looks like after 15 centimeters. Convolving against that is quite difficult. So now I'm going to talk about our new approach to this problem. So this is motivated by our belief that accuracy is important. And in this optics community, we're all interested in optical systems. And so if there's a component in the system, like your propagator, that's low accuracy, that will limit the accuracy of the entire system. So our hope is to remove this roadblock so that now it's possible to achieve higher accuracy in optical systems. So with the discussion up to this point has sort of suggested we ought to be looking for algorithms that have guaranteed accuracy, so that you can request ahead of time a solution that's correct to 8 digits and get a solution that's correct to 8 digits and have confidence in the answer. So we need to learn a lesson from these previous examples, and the lesson is as follows. You are going to struggle whenever you try to work directly with samples of your boundary data. And the reason for that is as follows. The field spreads out as it propagates. As it propagates, the number of oscillations per unit area stays relatively constant. But because the field is spreading out, U is going to contain more oscillations the farther you go. And if you try to represent an oscillatory function with samples, you're going to need a lot of samples. The lesson here is we should be looking for representations of the field whose complexity is determined by the complexity of your boundary data, not the propagation distance. And so now I'm going to talk about a representation that has that feature. First, I need to briefly discuss what we're going to do with evanescent waves. So the difficult part of the problem is dealing correctly with the propagating part of the spectrum. Dealing with the evanescent waves turns out to be fairly straightforward because in the Fourier domain, the evanescent part of the kernel is not oscillatory. So what I'm going to talk about, I'm only going to talk about the propagating part of the spectrum. If you happen to be working in a problem where the evanescent portion of the solution matters, you can account for it separately in a relatively straightforward manner. So the first thing to do is to switch to spherical coordinates. So now I've represented this three-dimensional vector x by its magnitude r, its polar angle theta, and its azimuthal angle phi. And then we make use of this expansion, e to the I x dot y, where x and y are three-dimensional vectors. And you can express that as this sum involving the spherical Bessel functions and the spherical harmonics. So if we substitute that expansion into the Rayleigh-Sommerfeld integral, you wind up with Whittaker's expansion of the field. So now, instead of writing the field U as this integral, it's rewritten as a sum involving the spherical Bessels and the spherical harmonics. These coefficients f hat and m come from your boundary data. So what you do is you take the propagating part of the Fourier transform of your boundary data, f hat, and you project it onto the upper hemisphere of the unit sphere, and then you integrate that function against the spherical harmonics on the upper hemisphere. So that's what that integral says in words. So that looks like the perfect answer to this problem. It kind of suggests a two-step algorithm. Step one is you take your boundary data, expand it using the spherical harmonics, and then step two is you just use that top formula there to propagate each spherical mode by evaluating the spherical Bessel function. Unfortunately, the step one is very inefficient, and that's because typical choices of boundary data have Fourier transforms that are concentrated in some region. Expanding functions like that in spherical harmonics tends to be very inefficient. In other words, we'd like to truncate that top sum. You can't sum to infinity. And it takes many terms in that sum before they decay to a small enough level that you can truncate it with high accuracy. So what we want to do is try to find a more efficient decomposition of the boundary data using basis functions that can still be propagated easily. So to do that, we turn to the generalized prolate spheroidal wave functions. And they were studied by Slepian and his collaborators at Bell Labs in the 60s. And they're a natural basis for working with data that is concentrated in some aperture and band limited. So in our case, to be definite, we'll say that our fields are concentrated in some square aperture of side length L, and they're band limited by some R. So because we've decided to deal with the evanescent wave separately, we can say that our band limit is at most 1, and in certain cases it might even be less. So now you introduce two operators. The first is this space-limiting operator, which looks like a Fourier transform, but it's restricted to the aperture, to the square aperture. And the second operator is the so-called band-limiting operator, which looks like an inverse Fourier transform, but it's restricted to the disk of radius r. So now we want to look at the so-called space and band-limiting operator, which is the product of these two things. We call that operator Q. And it's an operator of convolution type. And the convolution kernel K is given by the inverse Fourier transform of the indicator function of the unit disk. And it's given by this formula here, which just involves the Bessel function. And so the generalized prolates are the eigenfunctions of this operator Q. So the mu j is the eigenvalue, and the psi j is the associated eigenfunction. So to really understand these functions and this operator, you need to look at the spectrum of Q. And so here's one particular example of it. And what's kind of beautiful about this setup is that the eigenvalue mu measures the concentration of its associated eigenfunction in the aperture. So the eigenfunctions corresponding to eigenvalues close to 1 live almost entirely inside the aperture, and the eigenfunctions corresponding to eigenvalues close to 0 live almost entirely outside the aperture. What this means for us is that if we're looking at an optical field that's concentrated inside the aperture, we only need to work with the prolates whose eigenfunctions are close to 1, because those are exactly the ones that are also concentrated inside the aperture. So it means we can work with the finite dimensional subspace of functions. So the prolates are a very natural setting for many problems in science and engineering, and that's been known for a long time. But they have not been widely used, and that changed in the early 2000s with the appearance of a couple papers. The reason they weren't used is in order to expand a function in prolates, you need quadratures in order to do that. You have to use some kind of numerical integral to do this. And there weren't good quadratures for doing that. So we used the generalized Gaussian quadratures for band-limited functions to construct a discrete form of that continuous eigenproblem I just talked about. When you solve that discrete eigenproblem, you get approximate generalized prolates, and at the same time you get the quadratures you would need to work with them. And what that means is it's now easy to work with the prolate functions. So here's how that works. We have an algorithm that solves this particular quadrature problem. For a given band limit and aperture size, we construct quadrature nodes y and quadrature weights w that can integrate any function of band limit 2p with any desired accuracy, epsilon squared. And these are very efficient quadratures. The number of nodes you need is nearly optimal. So now, we take these one-dimensional quadrature nodes, build a tensor product grid out of them, and the associated tensor product weights. And that gives us a two-dimensional quadrature formula. So now, if you want to integrate two functions, f and g, that are band-limited to the disk of radius r over the aperture that's a square with side length L. You evaluate your functions on these grids, you multiply them by the quadrature weights, and add them up. So that lets us construct a discrete form of this continuous eigenproblem. So we now replace this integral by a sum, and this is just a matrix eigenvalue problem. So you solve the matrix eigenvalue problem, and what you get are these psi j and mn's are the values of the jth approximate generalized prolate at the mnth quadrature node. So it tells you the values of the functions at the quadrature nodes. And these eta j's are the associated eigenvalues. So now we've replaced the continuous eigenproblem with the discrete one, and now we can work with these discrete versions instead to any desired accuracy. Now we have one more trick. If you take that discrete form of the eigenproblem and you move the eigenvalue to the right-hand side, this formula says that you can express the jth eigenfunction as a linear combination of shifts of that Slepian kernel K. So you can, with the appropriate rates, you can write the jth eigenfunction as a linear combination of those radial functions that involve the j1 of x over x. What that means is if you have some boundary data and you expand it using the first j eigenfunctions, you can re-expand it as a linear combination of shifts of that Slepian kernel. And the shift coefficients are just given by applying this matrix K to samples of your boundary data on the grid. And K is given by some stuff you can easily compute. So now we can actually use this to do high accuracy propagation. It works like this. You start with your boundary data and you express it using shifted kernels. We do that by, from physical considerations, choosing an aperture size, a band limit, a desired accuracy, and this parameter k that tells you how concentrated your field is inside the aperture. So k should be very close to 1. You construct the appropriate subspace of generalized prolates. You build that matrix K made out of stuff. And then you represent your boundary data as a linear combination of shifts of the Slepian kernel. So this can be done with arbitrary accuracy. So now let UK denote the field propagated by one of these Slepian kernels. So you just put the Slepian kernel at the origin and you figure out the field that would be generated by that. Because the Helmholtz equation is linear, the field propagated by our boundary data is just a linear combination of UK. It's what you get by propagating each Slepian kernel. So in cartoon form, that means you take your boundary data, you replace it by shifts of the Slepian kernel, and the shifts are by the red dots. Each red dot propagates this function UK, and then when you want to evaluate the field, you just add it up. So the last step is we need to evaluate UK. That turns out to be easy. You go all the way back to the beginning, and you substitute Whittaker's expansion for the field. And so there I have reproduced it. And it turns out that because the Slepian kernel is so simple, it's just the inverse Fourier transform of the indicator function of the unit disk, you can plug that into the appropriate integral. You evaluate the integral, and that gives you a series expansion for the field generated by the Slepian kernel. So this is a series involving the spherical Bessel functions and Legendre polynomials, and these numbers A of n are given by a formula that involves more Legendre polynomials. So stuff that is very easy to evaluate. So this expansion for the field has our desired properties. The number of basis functions you need is determined by the complexity of the boundary data, in particular the space bandwidth product of your boundary data. We have a simple formula for propagating each basis function, and the result is an accurate formula for the field at any distance z. So an example of this is to propagate a Gaussian beam. So you start with a Gaussian beam whose diameter is approximately 10 wavelengths. You pick some parameters that are appropriate for that choice of boundary data, and you ask for 8 digits of accuracy. We want to propagate this 1,000 wavelengths. And to compare our answer with the true solution, we use Whittaker's expansion to get a formula for the exact solution. And the result is our method is correct to 8 digits, exactly what we asked for. In fact, off-axis, it's substantially more correct. So on the left plot, I'm showing you the real part and the imaginary part of the field in blue and red, and then the magnitude. And the right part is a logarithmic plot of the error. So I've had the question before, why did you only propagate 1,000 wavelengths? Because that's not very far. It's because the blue and the red lines get so wiggly after you go 10,000 or 100,000 wavelengths that the picture is sort of impossible to look at. So you can go as far as you want. I just stopped at 1,000 so that the plot looked nice. So future work. Right now, we have a method that is accurate but not fast. So if you're given n squared input points and you want to evaluate the field at n squared output points, you have to include the contribution at each output point from all n squared input points. So the computational complexity is n to the 4th. So we're looking for a faster algorithm by either accelerating this summation or looking for a different way to discretize the Rayleigh-Sommerfeld integral. Now that we have one way of doing it, we think that there's probably other ways to do it. And so we're looking at alternative methods of also solving this problem. We're also interested in applications where accurate propagators matter. Many imaging modalities require you to propagate a field through free space. Some obvious ones are digital holography, interferometric SAR, and antenna testing, where you want to take near field measurements of the antenna pattern and propagate them to the far field so you can get the radiation pattern of the antenna. So we are searching for applications that can benefit from highly accurate propagation. If you have one, please let me know. And one of my favorites is the phase recovery problem. So here the goal is to recover boundary data from measurements of the magnitude of the field at some faraway plane. So in the usual setup here, the propagation distance Z0 is large with respect to illumination wavelength and aperture size, so the far field approximation is valid. And in that case, the magnitude of the field is proportional to the Fourier transform of the boundary data. And that's the sense in which people call this a phase recovery problem. So there's a few things that make this tricky. The first is that the solution is not unique, which makes any problem hard to solve. The second is that there's some physical considerations that enter into this also. It's sometimes impossible to place the detector far enough away from the example to truly get into the far field. Unfortunately, the typical algorithms used for phase recovery require this Fourier transform assumption, so you kind of have to make that Fourier transform, that far field approximation anyway. That also causes some troubles. So the algorithms often used are variations on the Gershberg-Saxon algorithm, and they tend to converge slowly. We think that one reason for that is the way that the mathematical problem is formulated. So we're exploring better formulations of this mathematical problem that make use of the prolates. And we're attempting to combine a different formulation of this problem with our method for accurate propagation to improve algorithms for phase recovery. Gosh. So I want to acknowledge the people and the funding that make my work possible and answer questions. I gave this at my comps talk and it went long, but they asked a lot more questions than you did. I'm sorry about that. I should have included more stuff instead of taking things out. Yes.
So I understand that you are applied math person, not a physics or optics person. But in physics and optics, if you look at the problem you are discussing, there are several distinct kind of physical regimes of propagation. There is quasi-static field, real near the aperture, wavelength distance. There's wave regime where you several wavelengths away, you have Fresnel diffraction, Fraunhofer diffraction. Near field, far field, different names for the same thing. So how does your technique fit in all this? What's the relation between physics we all know from physics 300 something and what you suggest? Where it doesn't fit and where it doesn't?
So I took this part out, but if you go back to faster this way. The easiest way to see how it fits, you can start here, is to do an asymptotic expansion of Whittaker's formula. So what we're essentially using is Whittaker's formula over and over again for a particular choice of basis functions. So you can see everything from Whittaker's expansion. If you do an asymptotic approximation of the spherical Bessel functions with cosine of x or sine of x over R.
What's the large parameter?
So the large parameter would be R with respect to, well, anything. And then you can recover the far field approximation.
So, large R is many wavelengths. Or, in other words, it's a short wavelength. And everybody knows for short wavelengths, geometric optics is the answer. Can you comment on that?
all-
And objects is very efficient, very simple.
How do I want to answer that?
500 years.
So our expansion will give you a correct answer anywhere. If you happen to be in the extreme far field, you could probably use an FFT. And that will be faster than what we're doing. I mean, absolutely. If you happen to be in the extreme near field, geometrical optics will probably be faster than what we're doing. If you happen to be somewhere in the middle, you're going to have to work one way or another.
I think you should kind of frame this what you just said, a little more clear in your presentation, I would suggest.
Okay.
Yeah, because people know physics better than you take a functions.
Sure. Yeah, I see what you're saying. I mean, we're offering an expansion that's good anywhere.
But costs a lot.
Well, it costs, in the kind of ranges where very near field and very far stuff don't apply, I don't think it costs, if you want an accurate answer.
Diffraction, parabolic approximation.
Sure, and they will give you an answer that is sort of accurate. So you can very quickly get a wrong answer.
You have to show that you can actually deliver something that nobody else can. For a reasonable cost.
I kind of think I did that. I mean, I think.
I'm just not sure where it fits because there's little more than just near field and far field there. If you think about it, about a couple dimensional parameters, one is the one you're using, another is a null number, and they are related somehow, but not exactly the same. And different regimes have different length.
Okay, that's good advice, and I'll think about a way to include some of the more familiar physical concepts into this. Thank you. Yes?
How long does it take to calculate one information for typical cases?
So, sort of the first step is you can almost think of this as a matrix. You have a matrix that tells you how to take your input points to your output points. Generating that matrix takes a certain amount of time, maybe 30 seconds or a minute. And then once you have that matrix, you can apply it to different choices of boundary data over and over again. So that is just a matrix vector multiply, which can be done for medium-sized problems quite rapidly. So if you want to do the same propagation problem, same distance over and over again, that's pretty quick. You have to do some upfront computations, and then you can reuse them on different choices of boundary data. So I mean, the answer is to build the matrix, 30 seconds, a minute, 2 minutes, depends on the size of your problem. Once you have the matrix, it's how long it would take you to apply a matrix of that size to a vector.
If you already have this matrix compared with FFT, how much longer or shorter is it?
Sorry, I didn't catch the last part of your question.
You already have this matrix calculated for this distance and for this wavelength. How compared with FFT, how long does it take?
So let me be careful when I answer your question because I want to insert a caveat. So it would say if you're going a long way, say you're going 1,000 wavelengths or 10,000 wavelengths or something, you can't just apply the FFT. You need to do something else to keep your kernel from getting highly oscillatory.
If the distance is much longer than the relay range of the sample, it is okay. I mean, the approximation is accurate enough.
But then are you talking about like a far field approximation kind of thing? Okay, so if you're in the far field and that far field approximation applies, then you could use an FFT. And so the answer is an FFT on an n by n matrix takes n squared log n squared operations. Ours would take n to the fourth. At this point, I mean, we are very interested in accelerating our algorithm. This is a work in progress. They haven't let me graduate yet, so I've got some more work to do.
There are no more questions.
Thanks.